In this lesson, we will relate exponential functions with different bases by using transformations. So for example, in 1a, we're asked to state the transformations applied to f of x to obtain g of x. So what did we do to f of x to obtain g of x? But it's hard to answer the question at the moment because the bases are different. The base of f of x is 2 and the base of g of x is 4. So what I'm going to do is, since I want to know what transformations are applied to f to obtain g, I'm going to change the base of 4 to a base of 2. So 4 is 2 squared. Wait a minute, power of a power. So let's multiply the exponents. So yes, g of x is equal to 2 to the power of 2x. Now since f of x is 2 to the x, I'm hoping you can see using function notation that g of x is equal to f of 2x. G of x is equal to f of 2x, right? Because it's, if f of x is 2 to the x and g of x is 2 to the 2x, then g of x is f to the 2x. And since g of x is equal to f of 2x, then what can we say? What transformation did you apply to f of x to obtain g of x? It must have been a horizontal compression by a factor of 2. Right? Because the k value is 2. So that's why you want the base to go from 4 to 2, because now you can express g in terms of f. Alright, so we're going to do the exact same thing over here for 1b. So yes, you have 3, but I really want a base of 9. Well, 3, root 9 is 3. And based on what we learned earlier about rational exponents, square rooting 9 is same as 9 to the power of half. Power of a power, multiply exponents. So if that's the case, then g of x is f of half x. And since g of x is f of half x, then we know that we must have applied a horizontal stretch by a factor of 2. Alright, let's keep trucking along here. Okay, this time the bases are the same. But, 1 over 64. You know what? 1 over 64 is 4 to the power of negative 3. And if I'm multiplying two powers with the same base, I can add the exponents. That's the product law of exponents. Wait a minute. Everything looks the same except for the exponent. It's x minus 4, x minus 3. So g of x is really f of, let's see, hold on. If I have x minus 3, it's f of x plus 1, right? If it's x plus 1 minus what? X minus 3. Yeah, exactly. You can just sub it in on the side if you want, f of x plus 1, and you'll see that it's the same as g of x, because x plus 1 minus 4 will give you an exponent of x minus 3, which is what you want. Okay, so since g of x is equal to f of x plus 1, I can tell you exactly what transformation I applied to f to get g. Horizontal translation, 1 unit left. All right, let's keep going. So I have a base of 3 over 2, a base of 9 over 4. Well, I don't really like that 9 over 4. I need to relate it to 3 over 2. Oh, 9 over 4 is 3 over 2 all squared. Power of power, multiply exponents. I'm gonna factor out the -1 from the exponent and see what happens. You're really just keeping an eye on f of x and seeing like what you just really want to compare f and g and try to make them as similar as possible. All right, so okay, oh, everything's the same except for the +2 here and the factor of -1 here, right? So g of x is really f of -x plus 2. Since g of x is just f of -x plus 2, I can tell you what transformations I apply to f to obtain g. You have to apply a reflection with respect to the y-axis, and you're going to follow that up with the vertical translation 2 units up. All right, I want a base of half, but you know what? I'm going to use my negative exponents to help me out here. Negative exponent, reciprocal of base. Oh, that's not bad. So g of x is equal to -3 f of x plus 2 minus 1. Oh, wow. Lots of transformations going on here. So since g of x is equal to -3 f of x plus 2 minus 1, therefore we have a vertical stretch by a factor of 3. We have a reflection with respect to the x-axis. We have a horizontal translation 2 units left, and we have a vertical translation 1 unit down. If you apply those transformations in that order, to f, you will get g. All right, last one. Oh, this one's so silly. I can make the argument that this last example is the easiest. I can just quickly say, this one, the base is the same. Oh, this is so silly. This one's just like our previous lesson. There's nothing to do. The bases are the same. A is 3, K is, H is, 3, A is 3, and D is -2. So this is like the best case scenario. There's no algebraic manipulation required. And there you go. So we're gonna do actually one more thing and stay on the path. Okay, so this is the last example, but I actually want to do one more small little thing about transformations, and I'll do it on the back side of this sheet. So for the last little thing I want to talk about with transformations of exponential functions is the fact that you can actually group a lot of the transformations together because of the exponent laws that you've learned earlier. So let's start off with the fact that f of x, so we're going to transform a simple exponential function. I don't know what a, k, d, and c are, but whenever you transform an exponential function, it should look something like this. Okay? And now, based on the fact that the exponent here is k times all of x minus d, I can rewrite this using the power law of exponents, right? And x minus d, wait a second, I'm going to express this as a product of two powers. Now usually you simplify it into a single power. Here I'm going to express it as a product of two powers. Okay, because they have the same base, so hopefully this is not that bad. Okay, so I broke it to two powers, and if you want, you can simplify it back to the second line, but there's a reason why I want to express it as a product of two powers with the same base. Because I'm going to rearrange this so this is beautiful. Okay, this is beautiful. Let's circle this. I don't know what A, B, K, and D are, but that basically allowed me to combine all the transformations. Okay? I've combined the horizontal stretch and compression. I've combined the horizontal translation and the vertical stretch into a single transformation. So really, why is this very powerful? Because if someone were to give me a graph of an exponential function, I can find the equation relatively quickly. Let's say this is 31. Okay, so normally what you have done before I showed you this beautiful relationship, you would be like, oh no, I gotta solve for A, K, D, and C. That's a lot of work. Well, in fact, you don't have to solve for A, K, D, and C. Because we are going to group the transformations just like we did over here. You really have to just solve for A, B, and C. Okay? A, B, and C. And luckily, you have the horizontal asymptote. So since the horizontal asymptote is y equals 4, therefore C must be 4. Okay, the vertical translation must be 4 units up. So we have two parameters left. We have A and we have B. Well, I have a y-intercept of 5. You know what? Why not use that? So f of 0 is 5. Beautiful. A is 1. So you know what I have now? Is f of x equals b to the x plus 4. Well, I need to solve for b. So let's sub in the point 331 and let's see where it takes us. Hey, what do you know? B is equal to 3. So what can I conclude? The equation is, where was I? 3 to the x plus 4. So hopefully you notice how beautiful this solution is or this approach, because you've combined the transformations. Instead of working with A, K, and D, you just have to solve for A. And this all comes from your knowledge of exponent laws. And don't forget to solve for the base though. Okay, so solve for C using your horizontal asymptote, solve for A and B using 2 points, and then you're done.